This meeting is being recorded.
In section 5 of chapter 14, we're going to take a look at the next characteristic of our stretches and our spectrum. Now we're going to take a look at the shape and kind of compare whether or not we see a broad signal or a narrow signal. So we're told here IR signals can be broad or narrow, depending on the specific stretch, the specific wave number, the frequency of that stretch. So we're going to see that we have an OH stretch signal that we're commonly going to see that being quite broad. So something that looks like the image on the left, we're going to see with OH stretches of alcohols in particular. But we can also see what's referred to on the right-hand side here as a narrow signal. Sometimes these are referred to as tongues. You can see why, right? These are a tongue shape, and these are sometimes referred to as swords. So we have our broad signals, our tongues, and we have our narrow signals, our swords, to review here. So a common OH stretch, like I mentioned before, this OH bond in an alcohol, can be changed depending on whether or not we have a dilute or a concentrated sample. So when we have hydrogen bonds form in a sample, our OH stretch is this bond is weakened. So that's why we produce that broad signal with our alcohols. But if we include a solvent that can dilute our alcohol solution, and the solvent is incapable of hydrogen bonding, then we can actually produce an additional signal, a very narrow or sharp signal. So let's take a look at this case, both of these cases. So again, we can produce two signals for this OH stretch. So our alcohol that's capable of hydrogen bonding can produce this type of signal shown here. So this broad tongue, if you will, is indicative of the OH stretch for hydrogens that are participating in H bonding, or groups that are participating. And then we have in our dilute sample, if we dilute again with a solvent that is incapable of hydrogen bonding, we can produce what we refer to as these free OH. That produce this signal shown here. So again, you should note not only what the signals look like, but also when they appear. So the normal presentation or the dilute alcohol that produces that free OH signal. So an OH stretch can look differently when it's a different functional group. So we saw, let's go back real quick. We saw this range here for our alcohols, right? So up to about 3,600. And we start, let's see, right about here, so around 3,200. But we can see that our carboxylic acid, the wave number starts around 3,000 rather than 3,400 reciprocal centimeters for what they refer to as a typical OH stretch, so that of an alcohol. But now we have this OH stretch in a carboxylic acid in this area here. And we also produce, remember, carboxylic acid has a carbonyl as well as the OH group. So we saw this OH stretch. We can also have a signal of our carbonyl, and that's what's shown in this region here. So we can see that's around 1,700 or so. So we're going to see CO stretches in this range here. And for this example would be with a carboxylic acid. And we're also going to see OH stretches for both carboxylic acids and alcohols in this region more to the left. So when we see this shape, we can sometimes see H bonding happen with carboxylic acids in the sense that they can actually form a dimer here. So when we have our alcohols, they can hydrogen bond with themselves, but carboxylic acids actually can bond in two locations to form these dimers that we're referencing here. And that's why we have these, as they're referred to, more pronounced H bonding representative signals shown. So that's why it's an even broader signal than our alcohol. So when we talk about shape, we can also reference amines. We're going to see some characteristic patterns of both primary and secondary amines. These will both exhibit an NH stretch signal. And then again, these NH bonds are also capable of hydrogen bonding, so we can see broadening of signals. And more specifically, we're going to see for secondary amines, we're only going to have one signal, whereas primary amines, we're going to see two signals. So let's take a look at why in the spectra shown on the next slide here. So what we have on this side here on the left is going to be a primary amine. And then what we see here on the right, we can call this a secondary amine. So let's quickly review why. The nitrogen is bonded to one R group in our primary amine. It's bonded to two R groups in our secondary amine. So what happens? We have this NH, two NH bonds here, and then we have one NH bond in our secondary amine. So let's see the rationalization behind why we see either one or two signals. So when we have a primary amine, here we have hexylamine shown, we see that these two NH bonds vibrate together in two different ways. So here's one of those NH bonds, here's another NH bond indicated, and we can see either symmetric stretching or asymmetric stretching for those same bonds. But at any point in time, half the molecules will be stretching one way and the rest will be stretching in another way. And that's why we have these two signals shown for a primary amine, whereas we only have a single signal shown for a secondary amine. So you can remember there's two NH bonds in a primary amine. We're going to have two signals. And then you can remember there's only one NH bond in a secondary amine. We're only going to have one signal. But they would both have those signals appear in a similar range, somewhere between like 34, 3500. So we'll continue with our discussion on how to analyze IR spectra in the next video.